So the last thing I want to talk about is frequencies of interest, like the pole frequency and the cutoff frequency, and what they have to do with K values and these tables in section 19-5. I found these really confusing until I worked myself through an example. So I'm going to do that for you now. In order to demonstrate how this works, I'm going to make two circuits in Multisim, and they're both going to be low-pass equal component filters. So the gain on both of them, if you take a look, I have a 19K and a 10K on both of them. So the gain of both of them should be 2.9. The Q then would be 1 over 3 minus 2.9. That would be 1 over 0.1. So the Q on both of them is 10. The pole frequency on filter number 1 here is going to be 1 over 2 pi RC. That's going to give me a value of 1 kilohertz. So the top one has a pole frequency of 1 kilohertz, and the bottom one is going to have a pole frequency of 10 kilohertz. Let's take a look at these in Multisim and see what that means. So I've entered both of these circuits into Multisim, with the only difference being that this one here has 20 nanofarad capacitors and this one has 2 nanofarad capacitors. Let's open up the frequency response on the Bode plotter and see what the response of the top circuit is. So here we can see that the peak frequency occurs in around 1 kilohertz, and it's about 29 dB high. And then the 3 dB down point, well, that occurs in around 1.55 kilohertz. Now I'm going to open up the frequency response of the bottom circuit, and what we find is that it's essentially the same shape, except that everything has been pushed out to a 10 times frequency. The peak frequency is now happening at about 10 kilohertz, and it's reaching a peak of about 29 dB. The 3 dB down point is at about 15 kilohertz, 15.5 kilohertz, and they're at 3 dB down below the nominal value, which is over here. And that makes sense because the peak output is determined strictly by the Q value, and the pole frequency is strictly determined by the R's and C's in the filter circuit. So the point at which things happen is determined by these components, and how high things go depend on these. Now, before we look at the table, let's remember that the Q was 10 and the 3 dB down point was about 1.55 times the peak frequency. So the leftmost column here is Q values, and I'm going to go down here until I find Q of 10, which is our circuits that we looked at in Multisim. And then when you go across, there's these different K values. And what those are is multipliers that you would multiply the pole frequency by to get frequencies of interest. So the K3 multiplier will give you the 3 dB down point, and the K3 multiplier is 1.55. So if I take the pole frequency, if I multiply that by 1.55, I would have my 3 dB down point, which is 1.55 kilohertz. And that agrees with what we measured in Multisim. If I take my second circuit, which had a pole frequency of 10 kilohertz, and I multiply that by 1.55, the K value multiplier, I would get that its 3 dB down point was 15.5 kilohertz. So the reason these K values work is that if you have a second order filter with the same Q value, then it will have the same shape. And that means that everything that is of interest is the same multiplier of the pole frequency. So you can apply these tables to any second order filter. As long as you know what the Q value is, you can figure out where the 3 dB down point is. K value and ripple depth tables are really useful for understanding that frequency response is proportional to the pole frequency, but they've lost a lot of relevance in today's world since we have simulation tools that can do the job so much faster and easier.